This is recording.
RTI
International
Center for
Forensic
Science
presents
Just Science.
Welcome to Just Science, a podcast for forensic science professionals and anyone who is interested in learning more about how real crime laboratories work. In episode 8 of the 2019 R&D season, Just Science interviews Dr. Igor Lednev, professor of chemistry at the University of Albany, about using Raman Microspectroscopy and advanced statistics for detecting and characterizing gunshot residue. Dr. Igor Lednev and his team at the University of Albany are now using Raman Microspectroscopy to detect and characterize gunshot residue. Listen in as he explains how Raman spectroscopy works and the impact it will have on gunshot residue analysis. If you are interested in emerging drug topics, please visit forensiccoe.org to learn more about the upcoming NIJ Policy and Practice Forum on July 18th and 19th. You can attend in person or online. This season is funded by the National Institute of Justice's Forensic Technology Center of Excellence. Here's your host, Dr. John Morgan.
Welcome to Just Science, the podcast for forensic science professionals. I'm your host, John Morgan, the project director for the Forensic Technology Center of Excellence, a program of the National Institute of Justice operated by RTI International. Today, we are going to be talking to another individual who has given a talk at the American Academy of Forensic Science and the NIJ Research Symposium about some of the work that has been going on under NIJ funding in the research laboratory. And today's guest is Dr. Igor Lednev, who is a professor of chemistry at the University of Albany. His expertise is in laser spectroscopy for biomedical research and for forensic purposes. He has served as an advisory member for the White House Subcommittee on Forensic Science and editorial boards of multiple scientific journals, including, as relevant today, the Journal of Raman Spectroscopy and Forensic Chemistry. He is a fellow of the Society for Applied Spectroscopy and the World Society of Chemistry, and a recipient of the Society for Applied Spectroscopy Gold Medal Award, and has co-authored 210 peer-reviewed publications. He's going to be talking to us today about Raman Microspectroscopy and advanced statistics for detection and characterization of gunshot residue. And as folks who have paid attention in the last few years, there's a lot of interest in trying to improve the ability to use gunshot residue to detect who is a shooter and who is not a shooter using organic residues. And so we're very interested to see Dr. Lednev's work with respect to how Raman might be applied to that problem. Dr. Lednev, or Igor, welcome to the podcast.
Hello, John. Thank you for kind introduction. And by training, I am a laser spectroscopist. I have been working mainly in building new instruments and developing new methodologies for different applications, so in analytical and bioanalytical chemistry, specifically for disease diagnostics and for studying protein folding and aggregation. But when I joined University of Albany, our department started a new program, chemistry with focus in forensic science. This was both bachelor and master level degree. Our master students, they required research, so I was asked to start research in forensic chemistry, mainly for our master students. And introduction to forensic chemistry or forensic science in general, I received when I went to annual meeting of National Institute of Justice, and I found that forensic science has a lot of potential from the viewpoint of new method developments, in particular using laser spectroscopy, which can be applied at a crime scene, can be non-destructive and quite informative. We practically immediately started working on a project focused on identification and characterization of biological stains for forensic purposes.
Igor, did that followed on some of the work that you've done outside of forensic science too? So I assume you got your PhD from the Moscow Institute of Physics and Technology, I see, and I know that you had said before the podcast you've done some work with respect to Raman spectroscopy of blood and other biological specimens. And so what you're talking about with respect to applying these in forensic science was a natural extension of your other research work.
Right. The Raman spectroscopy has been known as the most selective spectroscopic technique. This is because Raman spectrum represent vibrational signature of material. Raman spectroscopy is based on so-called inelastic scattering of light. When medium, solid, liquid, or gas is irradiated with light, there is always scattering. And some scattered photons change energy due to excitation of molecular vibrations in the system. So if we analyze these energy changes for scattered photons, we get vibrational characteristic of material, which, as I said, is the most selective and specific characteristic of the material. So we can use Raman signature both for understanding the chemical and biochemical composition of material and can use it for identification purposes.
So Igor uses the term inelastic scattering, and for folks who haven't done work in this area, you can have if you think about elastic scattering, it's like if you hit a ball against the wall and it comes back with the same energy, that's elastic. Inelastic is if the wall absorbs some of that energy, so the ball comes back up at a different speed. And the same thing can happen with light. Usually what happens when you do that is that the vibrational modes, basically the modes of a crystal, have particular kinds of frequencies associated with the bonds in the crystal, and those bonds are very specific to the chemistry there. And the difference in the energy between the light that comes in and the light that comes out, this inelastic scattering, tells you what the energy of that bond is. Is that a reasonable description?
This is excellent description, John. Yeah, absolutely. This is
that I actually did some Raman spectroscopy as part of my PhD work as well. So I
okay.
Raman. Today's instruments are so much better than anything I had available to me in the laboratory. But it's an exciting thing to see this being applied in forensic science. So let's think about GSR then, and if you could just outline. Right now, GSR is limited to inorganic materials, which is useful to some degree, but has its limitations.
Yes, you're absolutely right, John. At the moment, scanning electron microscopy is used for detection of potential particles, and energy dispersive X-ray spectrometry is used in order to identify elements in these particles, and if lead, antimony, and barium are simultaneously found, it is considered that material is actually gunshot residue. And you can imagine that there might be some limitations for using this technology. First of all, there are environmental contaminations. For example, mechanics who are working with brakes and tires can have on their hands all three elements which I mentioned present. Although, as you also indicated, this methodology is limited to inorganic type of gunshot residue particles. However, there are plenty of organic gunshot residue particles also generated when firearm is discharged. And in fact, inorganic particles are larger in size, and it's easier to find them. As you described, Raman spectroscopy is actually based on vibrational characteristics of material. This means that we get information about molecules, their structure and composition. So we probe molecular composition of both organic and inorganic gunshot residue particles using Raman spectroscopy. And these Raman characteristics are very specific. For example, in one of our first publications, we looked at the possibility to link a Raman spectroscopic signature of gunshot residue to specific firearm ammunition combination. Our experiment was done in collaboration with New York State Police Crime Laboratory. Director Wickenheiser is our strong supporter, and police discharged 3 different firearms. We collected gunshot residue generated by these firearms, characterized with Raman spectroscopy, developed spectroscopic signatures, and then police fired these guns again. We take gunshot residue particles which we never touched before, and we identified with 100% confidence from which gun each particles came from. So you see, it's immediately, this example demonstrate how specific Raman spectroscopy is.
So you used 3 different kinds of firearms. My understanding is that you had a 38 caliber and you had a 9 millimeter. I don't know what the combination of the 3, but those were the types of firearms you were using?
Yes. Well, in that proof of concept experiment, both ammunition and firearms were different. So we just wanted to look, if you may, the simplest case scenario. But in principle, you can imagine that gunshot residue, first of all, should depend on chemical composition of ammunition, because particles composed of partially burned gunpowder. But we also have hypothesized that gunshot residue chemical composition should also depend on firearm itself, because combustion process which occurs when firearm is discharged is not complete, and it depends strongly on the conditions of the process. So we believe that the caliber and the type of firearm should also affect the chemical composition of ammunition. And this is one of objectives which we are working on now. We are trying to understand what is the role of firearm and ammunition and chemical composition of gunpowder in particular in determining the Raman spectroscopy of gunshot residue.
So Igor, let me challenge you a little bit here, because I think this is very interesting in terms of it being suggestive about what's going on. It reminds me a little bit of some of the former practice of bullet lead composition, where they're looking at, I think it was isotopic distribution of lead within different ammunitions. It was at one time used to try to distinguish one firearm from another. I know you're not looking at that particular issue, but I think it's important in this case to make sure we have a full understanding of the variability among firearms and ammunition types in order to truly say whether this is going to be distinguishing enough and persistent enough to be able to be used in practice. And I mean both of this separately, in terms of that there's enough differences among firearms and ammunitions, but also that it's consistent enough. Even a particular ammunition type can have variability in it depending upon manufacturer and practices in the manufacture of the ammunition.
Yes, John, I agree with you. This is a good point. Although, let me mention a couple of things here. First of all, our approach allows, even now, to help law enforcement agencies to exclude certain types of ammunition and firearm combinations as potentially used at a crime scene. Let me give you an example. If there is a short distance shooting, then victim will have some gunshot residue. And if police collected this gunshot residue from crime scene and they have a suspect with firearm in his possession, then we can discharge this firearm under laboratory conditions, collect gunshot residue, and show whether this firearm can be potentially used at a crime scene, and so we can exclude certain firearm and ammunition combination from being used. This is one thing. Second, in principle, what I told you that we can differentiate firearm, ammunition, and combination, it's just a demonstration at the moment, the power of Raman spectroscopy from the viewpoint of selectivity. However, the goal is to develop alternative technology for identification of gunshot residue, even without specific link to ammunition and firearm combination. You see, since we are able to identify both organic and inorganic gunshot residue particles, and we are doing it using much less expensive technology, it should help law enforcement agencies from this viewpoint, from the viewpoint of detection and identification of gunshot residue.
Yeah, Raman is much easier than SEM and X-ray spectroscopy to use. It's much cheaper, and you don't need a vacuum system or any of those kinds of things to use it.
Right.
So you're doing Raman where you're looking at individual particles or some subsets. Tell me a little bit about the specifics of your particular technique and how it would be applied in practice.
First of all, you're absolutely correct that we are using Raman Microscopy with a resolution of about 1 micron or submicron. So we can actually look at single gunshot residue particles. It is especially easy for organic gunshot residue particles, which are typically larger. Organic gunshot residue particles can be as large as 100 micron, and our resolution is 1 micron, so it's easy for us to do. In our earlier work, we did Raman spectroscopic mapping around gunshot residue particles, and we showed that we can identify and find gunshot residue particles on a relatively small area because Raman mapping is actually not very efficient technique because it takes time. But most recently, and I actually reported it first time at first meeting this year, we combined Raman microscopy with fluorescent microscopy. So practically, it's also two-step process like current technology where scanning electron microscopy is used to detect particles and energy dispersive X-ray spectrometry for identification. We use fluorescent microscopy to detect particles and Raman microscopy to confirm its identity. You may know that fluorescence spectroscopy is extremely sensitive. Single molecule can be detected using fluorescence. So we can do fluorescent mapping very quickly. And in our work, we showed that now we can map about 1 square inch of adhesive tape in reasonable time, find potential particles, and then look with Raman microscopy for identity of these particles. So this dual two-step process, I think, the most close to potential application in real world.
So are you doing both of those on the same instrument, or how's that working?
Yes, in fact, we are using the same instrument, and we are using the same laser excitation. The only difference is how we accumulate signal. Of course, fluorescent signal we accumulate much faster, and we are using objective with lower enhancement, so we can look at larger spots with fluorescence, because we just need to find particles quickly.
Okay, you've got me confused now, because your abstract says you're using Raman using a 785 nanometer excitation, which is pretty long wavelength. I wouldn't expect to see much fluorescence using that long a wavelength. But you said you're using the same laser for the fluorescence?
In our earlier work, we used only 785, but recently we started using visible light for excitation, and this is in part in order to combine Raman spectroscopy with fluorescence, yes.
Oh, okay. And can you shed light, if you excuse the pun, on which constituents of GSR are fluorescing? Because the inorganic wouldn't fluoresce, I wouldn't think, but I assume some or the other organic chemicals in particular fluoresce. Is that right?
Well, it's interesting, a very interesting question, actually. From our first experiments, actually, we found that both organic and inorganic particles are highly fluorescent. And even with 785, we saw some fluorescence. In fact, some particles fluoresce so much that it was difficult to measure Raman spectra because fluorescence interference. And it's not surprising because if particles are highly colored, then you may expect that they may fluoresce even with excitation in near IR. Now, of course, fluorescence is stronger if we are using shorter wavelengths for excitation, for example, in visible or near UV region.
Not unusual to have fluorescence and for fluorescence to be an issue when you're doing Raman work. I know one of the other applications for Raman in criminal justice is for drug identification in the field, and sometimes you have a certain opiate actually fluoresce a fair amount, and especially for some of those field units, they can have a hard time actually working well based on the amount of fluorescence that's being seen.
Right.
The fluorescence you're seeing at 785, not so much that it's interfering with your ability to collect a good Raman spectrum.
Well, with 785 excitation, we see some fluorescence also, and in fact, some particles, especially very dark black or brown particles, they actually fluoresce strongly even with 785 nanometer excitation. To deal with this fluorescence, we actually use ATR FTIR, attenuated total reflection Fourier transform infrared spectroscopy, as alternative to Raman spectroscopy, and we showed that, of course, since fluorescence doesn't interfere, we can detect with ATR FTIR all particles and characterize them as gunshot residue without exception.
Of course, ATR is a contact technique too, so it'd be nice to be able to do it all with Raman because you could do it non-contact.
Yes, you're correct. And also, ATR FTIR microscopy is quite slow. If we want to use it in forensic labs, then we need to combine it also with some technology to find particles.
So talk to me a little bit about collection, because this has been an issue that has been discussed in other frameworks for especially organic GSR, because I've never heard it quite discussed in the same way as what you're discussing it, that organic GSR can manifest as individual particles. A lot of folks have discussed it in terms of basically a vapor being deposited on the skin and even being adsorbed into the skin of some of these organic constituents, which of course raises issues with respect to how you collect that efficiently. It can have some advantages as well. So have you all been looking at the collection side of GSR and how that might impact your approach?
Well, at the moment, we are using one of the approaches or methods which law enforcement agencies are using. We are using adhesive tape to collect gunshot residue particles. So far, it works quite well for us. We can easily transfer gunshot residue particles from targets which we are using for shooting to adhesive tape, and it works well both for organic and inorganic particles. And most recently, New York State Police also discharged firearms for us, and we collected gunshot residue particles from hands of the shooter, and we also collected both organic and inorganic gunshot residue particles, no problem. And as I mentioned, organic particles are typically size between 1 micron and 100 microns. So the larger particles you can see almost with naked eye. And of course, it's easy to see them under the microscope.
Try to remember all of the different organic chemicals. Ethylcentralene comes to mind. There's several others. Is the size of the particle dependent upon the chemical constituent of the residue, or which chemicals exactly from organic residue are you seeing? And are you seeing differences with respect to what kind of particles the morphology of the particles that you're picking up?
There are some publications on morphology of gunshot residue particles, but we are mainly looking at chemical composition, and organic gunshot residue particles are mainly composed of partially burnt and unburnt gunpowder, and some of them contains also unburnt and burnt propellant. Inorganic gunshot residue particles contain some salts of metals, which I mentioned, barium, antimony, and lead. So as concerns fluorescent components, we actually don't know, and I discussed this question at the AFS meeting, and there are some suggestions that it's oxidized gunpowder, but this is something we need to investigate. I don't think there is a literature on what components actually fluoresce in gunshot residue particles.
Okay. So you're not picking up stabilizer materials from the ammunition, from the powder?
Oh, yes. This is actually one of the objectives of our current NIJ grant, that we are trying to link Raman signature of gunshot residue to chemical composition of ammunition. But this work is in progress.
Okay. I'd like to revisit a little bit just so people can get a feel for kind of the approach that you're taking from an experimental perspective. And you've examined the data using different techniques with the Raman and the fluorescence spectroscopy. You've looked at a couple of different kinds of ways of collecting it, either directly or from an individual. You've looked at different firearm combinations. But you also have been taking all that data and examining it with various statistical methods so that you can come up with some kind of confidence level, I assume. So can you tell me kind of, how you're doing your data analysis and kind of what this very bold statement you're making about being able to exclude firearm ammunition combinations, what the basis for that is from a statistical point of view?
One of the advantages of our approach that we can provide confidence level for our conclusions. And when I mentioned that we can differentiate specific firearm ammunition combinations based on gunshot residue analysis, the work was done in the following way. New York State Police fired different firearms for us. We collected gunshot residue particles, approximately between 50 and 100 particles per individual discharge. And we characterized these particles, and we built a statistical model which allows to differentiate spectra from 2 data sets or 3 data sets, depending on how many firearms we are considering. Right? So specifically, we used the partial least square discriminant analysis to build a statistical model for differentiation. Interesting thing here is that if we combine in one model organic and inorganic gunshot residue particles, then a differentiation actually is not as good if we consider organic and inorganic particles separately. And to some extent you can understand it, because when you try to combine in one data set two types of particles which are very different, then you sort of enlarge the potential variations in this class. However, if you consider each class which is narrow, then differentiation actually can be increased. So using this partial least square discriminant analysis, we actually built a model which allowed us to differentiate with 100% probability newly obtained gunshot residue particles, which we didn't use for in a training data set to develop the model. But as you know, statistical models like PLSDA, they allow you to estimate error rate when these models are applied.
All that's interesting, mostly from the perspective of there is a method to be able to analyze gunshot residue that takes us beyond the qualitative. So using your statistical approach, we can actually come up with some kind of quantitative analysis that ends in a confidence level and can be used to create error rates within this particular approach to GSR analysis.
I think so, yes.
So that's a good answer, actually, because we are, and I don't want to mislead people in the sense that I think these are very, very promising research studies, and I think there's some real implications with respect to the field. But there's a lot of work yet to be done to make sure that this is really ready for prime time in the crime laboratory. So along that line, can you tell us kind of where your research directions are right now? So you're wrapping up your NIJ grant, and we certainly appreciate NIJ's support for this research work, which is really outstanding. But you intend to continue this research work. Tell us kind of what next steps you're looking at in terms of bringing this forward.
Well, first of all, during this 3-year funding, we accomplished quite a few important objectives. However, we are still not ready for complete commercialization. We are still working on understanding the Raman spectroscopic signature. In particular, we are working on correlation between Raman spectroscopic signature of gunshot residue and chemical composition of ammunition. Secondly, we are working now with a company who expressed potential interest in developing instrument which would be using our approach. By the way, we already received one patent, and second patent should be issued in the very near future because our claims were approved. So we are working with company practically in order to develop software and hardware combined in one instrument for these purposes. And then, of course, the major step will be validation by practitioners using real field samples.
Well, that'll be really exciting. Are you anticipating that the instrument will include both the Raman Microspectroscopy or spectroscopy and the fluorescent microscopy as well in the same instrument in this regard, or is that what you're anticipating for the instrument you're developing?
Yes, at the moment, this is exactly the scheme we are trying to develop with company. The combination of fast fluorescence mapping and identification using Raman microscopy, yes.
Excellent. Well, we'll be looking forward to that. I think a lot of folks out in the forensic community will be very excited to see that and want to be part of the validation. This is an area, and I think you touched on it, and I don't want to overstate, but certainly it is an area where I feel the field is looking to try to get more confidence in the ability to distinguish various, not only different GSR combinations from different firearms, but really even just like having a good confidence about whether an individual even has GSR on them of any type. And so certainly very welcome research in the field.
Yes, I hope that we should be able to help law enforcement agencies with this new technology. And first of all, we hope that our technology will be less expensive and much faster. And potentially it can be used at a crime scene because Raman spectrometers, even Raman microscopes in the portable version are commercially available now. So moving to the field for identification of gunshot residue may actually help significantly because as you may know, one of the difficulties with gunshot residue analysis at the moment is secondary transfer. For example, if suspect was arrested and he was in police car, which contains a lot of gunshot residue already, then it is very difficult to make sure that gunshot residue which he may have on his hands comes due to the shooting and not as a secondary transfer. So all these aspects can be approached with a portable instrument.
Yeah, there are difficulties, of course, when you're trying to do a portable instrument of this type. I know that in general, when Raman has been applied for drug identification, they've preferred to keep the instruments in local police precincts and not actually out in the field, just because it's just easier to maintain them. The other issue that they've had is that the fieldable instruments, in order to make them work well, it takes a lot of good work to understand the signatures because generally the fieldable instruments have poor wave number resolution than what you're doing in the laboratory. Therefore, if you're looking at like 8-wave number or something, or even 12, I think some of the fieldable instruments you just don't have as quality a spectrum as you might have in the laboratory spectrum.
Yes, John, you're absolutely correct. What I would like to mention is that with a different company, we are working on actually trying to evaluate portable Raman microscope for biological stain identification and characterization. And actually it works quite well. We tried several handheld instruments which do not have objectives, so they do not work as microscopes. Those are very difficult to use for trace evidence. But portable Raman microscope, which we tested, actually works quite well for body fluid trace identification. So we haven't tried that instrument for gunshot residue, but I think there is a potential.
Well, we'll be paying very close attention to your work going forward, and it'll be really, really exciting to see how things develop. I certainly appreciate you taking time with us today to kind of give us a snapshot of where your research is right now and where it's heading.
Oh, thank you very much for your interest and for the opportunity to talk to you. And yes, I would be happy to continue our discussion.
So our guest today has been Dr. Igor Lednev, a professor of chemistry at the University of Albany, talking to us about his use of Raman spectroscopy to examine gunshot residue, both inorganic and organic gunshot residue. Appreciate all you folks listening in. Please, if you are a listener to the podcast, make sure you give us a lot of thumbs up and positive comments on the podcast platform of your choice. And so thank you very much for listening today. And again, thank you, Dr. Lednev, for being a part of Just Science.
Oh, thank you.
Next week, Just Science interviews Dr. David Rivers about the detection of insect stains and the development of quantifiable confirmatory tests to detect fly contamination of bloodstain evidence. Opinions or points of views expressed in this podcast represent a consensus of the authors and do not necessarily represent the official position or policies of its funding.